In this video, we're going to be talking about bonding, such as ionic bonding and covalent bonding, and we're going to touch on hydrogen bonding as well. But to start out, I'm going to talk about the periodic table and show you a couple of tricks on how to better read the periodic table so you can use it to your advantage. So to start out, when looking at the periodic table has these numbers for the columns. And the numbers above the columns are going to tell you something specific about the valence electrons associated with these elements. So if we're looking at column 1 and we see that there's hydrogen, lithium, sodium, potassium, rubidium, cesium, francium, these elements are all in the first column. Now, they're all in the first column because of a very specific reason. They all have a valence of 1 electron. Now, if you were to draw out the electron configuration for each of these in column 1, you would notice that, yes, indeed, each of them have 1 valence electron. So if we move on to column 2, the same thing happens, except for with all of these elements like magnesium, calcium, strontium, they all have 2 valence electrons. Now, if we move on to column 3, does this little pattern continue? No, it does not. It doesn't continue for all of these elements for columns 3 through 12. Now, 3 through 12 are special elements that you won't really have to deal with in this class, but this pattern does continue on if we skip over to column 13 through 18. If we start at column 13, the valence electrons are not going to be 13 valence electrons. It's actually going to be 3 valence electrons, and then 4, and then 5, 6, 7, and 8. Next, I want to show you the pattern of electronegativity. So electronegativity tells you how badly an element wants to hold or steal electrons. Now, if something's more electronegative, such as oxygen is very electronegative, and it's paired with something that's a little more electropositive, such as hydrogen, then the electrons that hydrogen had are going to be stolen, or in other words, hoarded. I think hoarded would be a better word for this. They're going to be hoarded by oxygen. Now, what is the pattern associated with this? Well, when it comes to electronegativity, the higher up you are on the periodic table and the further to the right you are on the periodic table, the more electronegative the element is. So fluorine would actually be more electronegative than oxygen. Usually you'll see an electronegativity scale written out as such in its simplified form. Oxygen is greater than nitrogen, which is greater than carbon, which is about equal to hydrogen. This tells you that the electronegativity starts out high here at oxygen and is low at hydrogen. So let's go ahead and talk about bonding now. And this specific bond that we're going to make is going to be ionic. I'll just let you know that now. But let's dive into it and figure out why it's going to be an ionic bond. So here we have sodium and we have chlorine. Now, in order to make an ionic bond, we need both of these to be an ion. And in order to form an ion, you either need to gain or give up electrons so that they are unequal with the protons that are involved in the element. So as you can see, we have different numbers of valence electrons in these elements. Now, with the number of electrons that are in these valencies, we can tell what kind of bonding they're going to form with other sorts of elements. Now, specifically with these two, we notice that with sodium, it's a very weak valence because it only has 1 electron in its valence. With chlorine, we notice that it has a very strong valence. Now, it's not completely strong. If it was completely strong, then it'd have 8 electrons in this valence. Now, being that it doesn't have 8 electrons in its valence, it has the availability to pick up an extra electron and form a chloride ion. In this specific instance, it's going to get its electron from sodium. Sodium is going to want to get rid of its electron because its valence is very weak. Since its valence is very weak, it's going to want to obtain a valence that's pretty strong, and the shell just under its last shell is completely filled. So that's where sodium's going to want to be. So it's going to kick off this electron, and chloride's going to pick it up. And when chlorine picks it up, it becomes chloride, giving it a negative charge because the overall charge is -1 due to it having 17 protons and now 18 electrons. That equals a -1. Sodium, on the other hand, got rid of one of its negative charges, and it has 11 protons and now 10 electrons. So 11 minus 10 equals 1, or +1. So being that we have a positive charge on the left and a negative charge on the right, these charges attract. And they will attract better if they're equal whole charges. And here, both of these have an equal whole charge, being that sodium has 1 positive and chloride has 1 negative. So these will associate with each other and form that ionic bond. Now, an ionic bond is really just two elements getting up really close to each other, just as if you were to make a fist out of both your hands and butt them up next to each other. So this is more of kind of the bond that's really being made. It's association between the two. They're just attracted to each other strongly. Now, when we talk about other bonds, such as covalent bonds, that's more as if you took your fingers and interlinked them, as if you were holding hands with your girlfriend or boyfriend. It's a much stronger hold, whereas fist bumping is not really a hold at all. So next, we're going to talk about covalent bonding, and specifically, we're just going to talk about polar covalent bonding, and hopefully you can figure out non-polar covalent bonding on your own. But we're going to use a water molecule for this. And we're going to make this a little simpler, a little easier by just looking at the periodic table and determining how many valence electrons there are and just drawing the valence instead of wasting time. So to start out, we have oxygen. And so we'll start by drawing a little O there. And let's go look at the periodic table real quick to see where oxygen stands as far as valence goes. And you can see right here, oxygen is in column 16, denoting that it has 6 valence electrons. So let's go back and give it 6 valence electrons. So let's put 1, and then 2, 3, 4, 5, 6. So you can already see that oxygen has the ability to pick up at least 2 more electrons. And with water, we have 2 more elements that we're putting into this, and those just happen to be hydrogen. And hydrogen, if you look at the periodic table, it's in column 1, and column 1 tells us that there's only 1 valence electron. So let's throw hydrogen into the mix. Put a hydrogen right here and a hydrogen right here. Let's put the valence electrons on there. So there should only be 1. There we go. So there's your valence electrons for hydrogen. Let me put this one a little closer to its hydrogen. There we go. That way you don't get confused. So just by looking at these valencies, you can see where the hydrogen's kind of going to fit in. Now, we ask the question here, is it going to be an ionic bond, a polar covalent bond, a non-polar covalent bond, and how can we tell? So previously we talked about ionic bonds and how it utilizes a strong valence and a weak valence to form ions. Here we don't really have a strong or a weak valence. We have two valencies, or three valencies, excuse me, that are near half full. Now the hydrogen valencies are halfway full. The oxygen valency is slightly above halfway full, but it's still kind of there. So these guys aren't going to participate in an ionic bond is what I'm trying to get at. So if it's not going to participate in an ionic bond, we need to look at the electronegativity scale, because the electronegativity scale is going to inform us on how to determine whether or not this is going to participate in a nonpolar or a polar covalent bond. So if we're dealing with oxygen and hydrogen, let's look at where those are on this scale. So oxygen is at the high point and hydrogen's at the low point. So that tells us that the electrons in this bond are going to spend more time with oxygen, telling us that this is going to be a polarized covalent bond, or in other words, a polar covalent bond, because the electrons are going to spend more time on one end of this bond, giving that edge kind of a charge. So let's show how these link up then. We draw in hydrogens where we're going to fit them into this molecule. And I'll use orange here to show the bonding. And let's get the other electrons in there, because in every covalent bond, electrons are shared. But in a polar covalent bond, they're shared unevenly, like we were talking about. So these electrons here are going to spend more time over on the oxygen end of the bond because of its electronegativity. Now, it's going to share the electrons even enough that it can still hold on to these hydrogens, but enough so that there is going to be a little bit of a charge difference here. So in other words, we're going to have polar ends. So if more electrons, being that they're negatively charged, are hanging out on this end, then you're going to see a slightly negative charge appear on this end. And then you're going to see the exact opposite charge form on the other side of this molecule. And this is what everyone's talking about when they talk about a polarized bond. You have polar ends, and these polar ends allow for bonding to take place, such as hydrogen bonding, and it allows for the great properties that you see within water or in like proteins and other things. So let's look at how hydrogen bonds are formed. So hydrogen bonds are formed when we have two polar covalent compounds or molecules that associate with each other due to their charges. Like we were saying before, these charges are not full charges like you see in ionic bonds, but they're partial charges. So they're not going to participate in any ionic bonding per se. What they are going to do is they're going to participate in weak bonding called hydrogen bonding, which is another association, not really a bond. So again, you could take both your hands in a fist and kind of put them together, and this is the kind of bond that we're going to make, but it's way weaker than an ionic bond. Looking at the charges in between these two, so we're looking at specifically this negative charge and this positive charge here. These are the two that are going to be at play. So since they are opposites of each other, they are going to attract each other, and since they're of equal charge proportion, they are going to associate with each other. And this association is going to weakly hold the two molecules together in what we call a hydrogen bond.